Welcome back, everybody. This is a set of questions related to Fall 20 Test 1, Part 4, spectroscopy. This question is actually related to a previous question. It's a general question about benzene. I think I can illustrate an answer with an example. Now, to answer her question here, how do you know which letter has a higher delta? Benzene typically is around 7.2. She said 7 point something. 7.2 would be the normal benzene, 7.1, 7.2, 7.3. I'm not that picky when you're signing in the big table question that's previous to this one, where you have to fill in letters A, B, C, D, E, F, G, H, I, J. I'm not that picky. If you're in the benzene region, I'm generally going to give you full credit. But I'll give you an example where they should, they should be separated by a little bit. So if I did this here and I have like an iodine here and like carbon group here and maybe an OH off of that. And I had to give this one and this one and this one, and I call those C, D, and I, just to match her letters. It wasn't the example that she was talking about. I would pick D to be the highest. Because it's close to an inductive atom. And C would be a little lower. If you reverse the order on C and D, I wouldn't deduct any points. My logic here is this is close to an inductive fluorine, pulling electrons away, making the gap between the two spin states bigger. It's also close to a carbon, which is more electronegative than this one, which is on this side next to a hydrogen, a little less electronegative. So carbon's got a teeny inductive effect compared to a hydrogen. This one's close to the fluorine, but the next atom that's close is not as electronegative as that. So I lowered it a little. And I, not that special. Iodine's not that electronegative. My carbon here was same electronegativity as iodine, but it has an O on it. And I would go with a slightly lower number for that one. But seriously, if you just played around with the order of these on a test, I'd probably just give you full credit because you found that it's H on a benzene, and that's the most important thing. Okay, so that was her question there. And then these sets of questions relate to the molecule up here. And she was asking why G is 1.8 allylic, why not consider it 1.4 to 1.7 R3CH? It's a good question. They're both in the realm of possibility. Well, it's not G here, is it? She's asking about probably the one from the previous page. If I see a 1.8, do I always have to think allylic? On the table, it says 1.8 is allylic. 1.8 is also real close to this. I can't rule this out. So I would have to consider it. Sometimes you're in, you have two possible categories and you just gotta try them both out. And the one that works is the one that wins. If the other doesn't work, then this one wins. And vice versa. And Jay, see, I didn't copy the right question down, did I? 5.4 ppm means vinyl internal Y. I considered RCH2 4.4 to 4.5. Well, this number is just too high to be an RCH2F. If it's 5.4, it can't be RCH2F because it's too high. So to be a RCH2F or any kind of RCHF, it doesn't really matter the number of H's. I think that question comes up later. The number of H's is not as important as you think. It's being in the right category. And she asked about, does an intense infrared absorption. Now, we don't teach any IR in this course, but the only thing I do, and it repeats over and over on exams, anything near that number means we have carbonyl. That's why I said she was close here. So get rid of that. Doesn't necessarily mean ester or carboxylic acid. It means carbonyl, which is a very useful piece of information. Carbonyls are found in a lot of functional groups. She's just looked at exams and noticed I do have a lot of esters on there. And yeah, I do like esters a lot. They're a very common functional group. So you have that. I suspect that we'll be doing one of these on, somebody's going to ask me to do one of these entirely. And that would be a good session right there. Yeah, sometimes it's possible to be in two categories and you've got to entertain the idea of each one and just see which one fits. Don't forget, you got to fit all the data. When I say all the data, I mean your peak's in the right delta that has the right number. It has the right pattern because of the neighbors, and it has the right height because of the number of H's. You got to make all three of those things work. Stick with our NMR theme. Oh, it's not an NMR theme. Where was the NMR theme? There we go. This is related, so we'll deal with this now. And she had one question on, or two here. For E, why did we do a baseline? Okay. In E, it's a little sketchy up here, but E is over here. I'll highlight it. Yellow highlighter coming up. E's up here. E is both benzylic and ether. Benzylic because it's on a carbon one away from a phenyl, and ether here. And sadly, I don't believe I have a copy of the test open anywhere, but I'm close. Yeah, I'm close enough. I do. I was ready. I just forgot I was ready. I'm just going to move on over here. It's from an answer key, but there we go. When you're benzylic, you've got this. And when you're in ether, you got this. Let's try snipping both of those. And get rid of that and get rid of that. Bring it over here. And we'll talk about the baseline in a second. Baseline's defined as, hey, pretend it's in none of the categories. Where do you even start? Because we want to see the effect of being in two categories. When you're benzylic, your peak is roughly 2.5. I don't care about the number of H's. We'll deal with that question down here. And when you're ether, this is not relevant here. When you're an H attached to a C in an ether, you're around 3.6. Now the baseline for E, that carbon has how many bonds to carbon? 3. 1, 2. Well, it has 3 groups attached. So my baseline should be everything not including those groups. So R and something else. I'll take either baseline, R3CH, or you could make an argument there aren't 3 R's there, Dr. Whitaker. RCH2R. It really won't change our answer too much. I'm going to bring back the chart. I'm going to try to bring back the chart. 1.2 to 1.4 for one of the baselines, 1.4 to 1.6. I'd make this 1.3, this 1.5. Does it really change my answer that much? Doesn't really matter if you choose the exact right baseline. In fact, why don't I use an average of the baselines? There you go. Now the effect of going from the baseline, which means there's nothing special, to being in an ether category is a jump of 2.4. And the effect of being in a baseline and then all of a sudden being benzylic is a jump of 1.1. You chose the baseline 1.4. That means that's your beginning. No special category. The combined effect of being ether and benzylic is 3.5. I just added these two numbers. 3.5. Give me an answer. Give me a pen. I wanted it green. Part of the answer comes from red and green. 4.9 ppm. Put that over there. 4.9. So we choose baseline when there's two categories that the molecule fits. It's going to happen one time on your chart, I promise. One time on the chart. And so if you miss it, guess what? You missed a third of a point because each line is worth a whole point. So is it going to be terrible if you miss that? No. Give yourself a pat on the back if you don't miss it. And down here, she's asking for N. Delta is 3.3 means RCH2OR, but here we have CH3OR. Before we answer that question, what's more important? What is more important? Inductive effects, that's the presence of the oxygen, or how many H's there are. So in these three examples from the chart, only the H's are changing. Are these big changes? 0.4 and 0.2. You add an oxygen, does it really matter how many H's are here? You went up to 3.7, not because of the number of H's, because of the inductive effect of the O. So I need you to be close to this number. It doesn't matter if it's CH3OR or RCH2OR. It's the same category, really. So 3.7 is your number. Or it's in the range. The range we found over here. Anywhere in there, I'm happy. Okay, you don't have one with a CH3 here instead of a RCH2. You don't need one. It's the O that's important. And I think that took care of her NMR questions. And after our little break, we're going to do a mechanism here, and it's an oldie. And it's an oldie with some critical thinking because it's the same mechanism as acid catalyzed hydration, except instead of using water, we use an alcohol. So look ahead at that in Fall 19, Test 1, Part 4, 3F, and I'll see you shortly.